presentation, and you can also participate and ask questions anytime at one of our meetups from the YouTube stream as well. Yeah, we found that in Mozilla Hubs, you usually have a capacity of about 25 to 30 people in a room. So we're getting close to that here with 22, which is great. We're happy to have everyone. And so that's just why I mentioned it, that it could happen sometime when you come to the meetup for the space that it's full, and then you can join the YouTube, and then you can always come back for the question and answer portion or rejoin the room at any time. We typically have people coming and going sometimes through the presentations. Another note while we're getting set up, one thing that's been great about hosting inside of Mozilla Hubs, we use this platform because it's the most accessible platform for social VR that we found to date. And I got notice from Elgin, who is one of the social community managers at Mozilla Hubs, that they're making progress on some of the bugs and feature requests that we logged with the Mozilla Hubs team. And yes, Joel, I agree, she's great. And she's been great about helping support our meetup and get it set up. And it's very nice to know that Mozilla does care about the accessibility of the platform. Just wanted to give you all an update that they are going through those issues. And Stacy, who's also here in the room with us, has been taking notes from each of the presentations that we have. So if you do have any accessibility feedback, requests, ideas at any of our meetups, we do collect all of those and share them with the Mozilla team. All right, so we're getting close to our starting point. So I'm going to do just the intro spiel one more time about using Mozilla Hubs, and then we will get started today. So inside of Mozilla Hubs, you have the ability to control the audio of individual speakers. And so the presenter today is Yuhong Zhao, and she is here up near the front of the room, floating a bit in the robot costume with the pumpkin on the front. If you move your mouse cursor over her avatar and hold the space bar down, you will have a plus and minus indicator to control the volume of her voice. And so because this room is quite large, we recommend boosting the presenter's voice pretty close to the top audio level, and that'll make sure that you can hear the audio really well in the presentation today. Another housekeeping request is that Jolie McPhee, who is the flying camera, kind of back a little ways in the room, that camera is actually filming the presentation and broadcasting to YouTube. So we ask that you just be mindful of where you're standing in the room so that we don't, please don't stand in front of the camera, because it will actually broadcast onto the YouTube stream and make it difficult for people watching the YouTube stream to see the presentation. With that, my name is Thomas Logan, and I want to welcome you all to the
Did the caption stop?
Oh yeah, we can get started. Oh, okay. We'll take one moment for the closed captioning. Oh, wait just one moment.
Okay, it's back. You're all clear to go.
Okay, great. All right, so my name is Thomas Logan, and I'm the host for Accessibility VR, and excited to see so many of you all here today for our October meetup. Our meetup is set up to explore having conversations about how virtual reality, augmented reality, extended reality, all of the new technology, how can it be made accessible and useful by and for people with disabilities. So every month we have this meeting in this space, and we're exploring those topics, and we look forward to always having new topics, new ideas to discuss with you in the community. We take the feedback that we receive from this meetup very seriously. As I mentioned, we work closely with the Mozilla Hubs team. We chose this platform because it was the most accessible that we could find, that what was able for most people to be able to access. If you have issues or feedback on how the experience could be improved, we do take that feedback seriously and we share that with the Mozilla Hubs team. We've been very happy that they've been working with us to help improve the accessibility of this platform. And so we always learn from every meeting that we do inside of here. We want to thank Jolie McPhee from the Internet Society of New York, who is streaming our event to YouTube. Every event that we do is streamed to YouTube, and all of the recordings live on, so that if you are interested in any of the past presentations that have happened at Ali VR, they all exist on YouTube. And if you need to see the YouTube today for any reason, if the connection cuts out, I've pasted into the chat for the room the YouTube link. And we also always post that YouTube link on our meetup page for your reference. We also want to thank Stanley Sakai, our getting confused here, our captioner today. His website is stanographer.com, and he is a captioner that we have worked with at our other meetup that's based in New York City, Ali, New York City. And we're very happy to have Stanley here today to have the captions for you. And that's also part of our meetup guarantee, is that we always have professional captions available for the talks so that people can fully participate who are deaf or hard of hearing, and also so that we have a great transcript of the presentations at the end. Now, I would like to introduce you to Yuhong Zhao, our presenter tonight, or today, depending on where you are in the world. Yuhong is a postdoctoral researcher at Cornell Tech, and she will be joining the computer science department at the University of Wisconsin-Madison as an assistant professor in January 2021. She has tons of interesting research around helping people who are low vision, and I'm really excited to learn about her work and have us all learn about her work. So take it away, Yuhong.
Thank you, Thomas. Hello, everyone. So glad to be here today, especially this is actually my first talk in virtual reality, so very exciting experience. So today I want to talk about my research on how I design augmented reality systems to make it better serve and empower people with low vision who have visual impairments, but also have usable vision. So first of all, I want to talk a little bit background about what is low vision. So by definition, low vision includes all kinds of visual impairments that fall short of blindness, but cannot be corrected by eyeglasses or contact lenses. And it's actually very complex and include many different visual conditions. So for example, this is the typical vision that a sighted person see through their eyeglasses. But if you have low vision, for example, if you have cataract, and then your vision can be very blurry, but this blurriness cannot be corrected by eyeglasses. And of course, there are many different low vision conditions. For example, people can have central vision loss, have blind spots inside their vision, or lose their peripheral vision. And these are just some examples, and there are many different conditions. And also a low vision person can have multiple conditions at the same time. And all of these bring a lot of difficulties to people's daily life. But the one interesting thing is, if you look at these images, you may also notice that all low vision people, they still have a lot of functional vision to use. And the fact is, most of them, they still prefer and actively use their vision in many important daily activities. And this actually has made low vision research more challenging, because it will not only involve technology innovation, but also a deep understanding about different low vision people's visual perceptual abilities. So there have been in HCI and accessibility research, there has been a lot of work that has been done for people who are completely blind or people with visual impairments in general. Most of these work, they focused on providing audio or haptic feedback to compensate for the impaired vision for people with visual impairments. but overlooked the fact that people with low vision, they still have functional vision to use. So there is actually a significant lack of knowledge on in the research field on how low vision people use their vision in their daily life, and how can we design suitable technologies to better leverage their functional vision and enhance their visual ability in their daily activities. So, but the good news is augmented reality technology has presented this very unique opportunity to leverage the functional vision that low vision people have. So, for example, with the camera automatically recognizing the surrounding environment that low vision people cannot perceive very well. AR technology can generate immersive visual augmentations to convey these recognized information, thus enable low vision people to better perceive their surrounding environment and complete different visual tasks. So my research goal is to leverage, to take this unique opportunity that AR technology has presented and explore how we can better leverage AR technology to enhance low vision people's visual ability. So there are two goals in my research. So one is to understand and explore low vision people's visual perceptions when they're using different type of AR devices, and also in different type of daily tasks. And based on their needs and the experiences, I also design and build different AR systems to enhance their visual ability directly by designing different type of visual augmentations to facilitate different daily tasks for them. And today I'm going to give two examples about how I do this in my research. And I'll start with visual search. So I start to explore this visual search task actually with an exploratory study where I observe how low vision people conduct a grocery shopping task. So this is actually a very typical start of my research, is to do exploratory study, because it gives me a really good context to understand the user's experience. So how I do this is I ask the participants to conduct this grocery shopping task. I give them a target product and ask them to find this the nearby grocery store, and also get into the store and find a specific target product and buy it. And during this process, I follow the participants, observe their behaviors, and also ask follow-up questions about what they can see, why they behave like this, and also what technologies they are using. And during this process, one most important finding I got is, well, low vision people encountered a lot of different difficulties during this whole process. But one of the most challenging and time-consuming tasks is to find the specific target from this crowded grocery store shelf, which is a visual search task. And how they usually do is they get very close to the shelf and pick up each item one by one and bring them very close to their eyes. Some of them also use a magnifier to look at the details and put it back and pick up another item. So they repeatedly do this process until they finally find the target product, which is a very long and low efficiency process. And during my study, I didn't find there were any effective tools that low vision people use for to facilitate this visual search task. So there is a really big gap there. So visual search is a very important and also fundamental visual task in people's daily life. And researchers have already designed different systems, came up with different solutions to address this problem for the general visually impaired population. So for example, there have been systems that leverage computer vision technology and also crowdsourcing to recognize a different product for the user and then generate different audio feedback to guide the user to the target. And also there have been systems that enable a blind person to scan the barcode on each of the product, and then they will hear the audio description of the different products. But still the user has to scan each item one by one until they find the target. So all these prior research in accessibility, they mostly focused on people who are completely blind and only provide audio feedback during this visual search process. But as I mentioned before, low vision people is different because they still have existing vision, and the visual channel is actually the most efficient sensory channel that they usually use to perceive the surrounding environment, especially in this visual search task. That's why different from the prior research. My goal is more about how to leverage people's functional vision and design effective visual augmentations to help them find a target more quickly and easily in this visual search task. So based on that, I designed QC, which is a new approach that are designed for people with low vision to help them conduct a visual search task via a direct visual augmentation. So if a user wears a head-mounted display that's showing the surrounding environment, and the system also has a camera scanning the environment, and then we can use computer vision to automatically recognize the different targets for the user. And then the system can render different visual cues to attract and orient the user's attention so that the low vision person can easily follow these visual cues to find the target. And now I want to show a video demonstrating how the system works. So first, the user can use speech command to speak out the name of the target and assign it to the system. So I apologize that this I cannot add audio to this virtual space, so I'm going to just describe whatever the human is saying. So she says, look for pea snack. So it's one of the products on the shelf. And then she will look around the shelf until the system recognizes a target and show the cues, and then she can follow the cues to find the target. So this is how the system works. But to accomplish such a system, the most important question we want to address is what visual cues should be provided there, right? So what visual cues would be effective enough for people with low vision? So this actually can be a very challenging problem because on one hand, we want the visual cues to be visible enough, but a lot of visual information that can be easily seen by people who are sighted are not that easy to be seen by people with low vision. For example, this image shows the blue cursor, which is a very typical visual cue on HoloLens. It's used as a cursor. But this is actually very difficult for people with low vision to see. And in this visual search scenario, we not only want the cue to be visible, but also want it to be obvious enough to attract people's attention immediately. And on the other hand, we also want to make sure that the cues are not too distracting that prevent the user from using their own vision to observe the surrounding environment. So for example, if a user has peripheral vision loss, it's like they see through a tunnel. So in that case, if a cue is relatively bigger, and then it can easily block the user's full field of view and stop them from using their own vision. So it is very important to think about how to balance the visibility and also the distraction when we design the visual cues. And of course, there are a lot of different low vision conditions, as I show at the beginning of the talk. So which means we probably also need to consider different design alternatives to fulfill people's different needs. So with all of these requirements, so what I do is I first work with an optometrist to deeply understand different low vision conditions and their needs. And I also look into some cognitive psychology theories to understand what visual stimuli can effectively attract people's attention. And by combining these different perspectives, I design 5 different visual cues to orient and attract low vision people's attention. So, but for the sake of time, I'm only going to give one example. So this one is called Flash. So it's designed based on the cognitive psychology that onset, which means the appearance of something can easily attract people's attention. And to amplify this effect for people with low vision, I add a frame around the target and also switch its color between gray and black to generate a continuous onset experience to orient and attract low vision people's attention. And of course, a low vision user can also select and combine different visual cues to customize their experience when they're using the QC system. So based on these visual cues, before we put a lot of time into the deep implementation, we first want to validate whether these cues are actually effective enough for low vision people. So to do that, I first built a prototype of QC by combining webcam with an Oculus Rift DK2. So this is a very old version of Oculus. Now they have a much better version that is a wireless version. So based on this setup, I also built a mock-up grocery store shelf with 24 different products on the shelf. But you may also notice that there are QR codes on all of these products. So this is because for this specific study, we only want to focus on the evaluation of the cues. That's why we want to minimize the confounding effect of the potential recognition errors so that we want to ease the computer vision process. That's why we just recognize these QR codes in our system. So based on this setup, we recruited 12 low vision participants and asked them to conduct multiple trials of visual search tasks in front of this grocery store shelf. And the participants conducted the visual search tasks in two conditions. One is QC with their preferred cues, and the other is their best correction as a baseline. And it means the user can wear their eyeglasses or use magnifier or whatever assistive tools they already have or they prefer to. So based on this study, so now I want to show two videos to compare low vision participants' experience when they use and not use QC. So first, when they are not using QC, using their original vision and their preferred assistive tools. So you can see that they get very close to the shelf and look at each item one by one. So this is actually a very long process. So it's a totally linear scanning process when they're trying to look for the target. And here he found the target. But as a comparison with QC, oh, that's the wrong video. Here we go. So now you can see he's wearing the head-mounted display, and it actually took him a much shorter time to find the target. So the comparison between these two videos demonstrated the effectiveness of the cues. But now we all know that this study was conducted in a very ideal situation where we only recognize the QR codes. So now we validated the effectiveness, the design, and then what if we build a system, a high fidelity system that actually use the computer vision technology, then how would that system affect the user's experience? Because we do want to consider how much the computer vision technology, including its accuracy and speed, would affect the user's actual experience. So to answer that question, I built the actual system of QC. So I first added a product detection component. So I used a computer vision module, which is a faster RCN model, which is a state-of-the-art computer vision object detection model. And I trained this model based on an RPC dataset, which includes 200 different products. So after the training, this algorithm actually got a relatively high accuracy with the mean average precision of 0.85, which is a pretty good result in terms of computer vision. And also, usually a deep learning module would not be fast enough to support a real-time interaction system. That's why I also added an object tracking component to speed the system up. And we also have a speech recognition system to enable user to interact with the system with speech, for example, assign the target to the system. So based on the implementation, we conducted a very similar study, but this time all the products do not have any QR code on it. So the system purely rely on the computer vision component of the system. So with the similar setup, we recruited another 7 low vision participants and asked them to conduct a similar visual search task, still in 2 conditions, QC and also their best correction. So during the study, we find that QC has significantly reduced the participant search time. So if you look at this bar charts, so it shows the mean time across all the participants when they do the visual search task in two conditions. The blue bar represents the time they used when they use their best correction, and the yellow represents QC. So you can see that the time was reduced to almost 1/3 of the user's original time, so which means it's a really big improvement. And also in terms of the search accuracy, and unfortunately the computer vision technology does make errors, so the final accuracy is not 100%, but still compared with the user's best correction, the system still improved the user's search accuracy from 83% to 95%. So QC is actually the first augmented reality system that automatically recognizes the surrounding environment and generate tailored visual feedback to enhance low vision people's visual ability. And different from the conventional low vision aids, for example, magnification, that are arbitrarily applied to the user's full field of view. The most important point I want to emphasize here is it is very important to, when we design visual augmentations, is to consider the user's context. For example, their different visual abilities and also the specific tasks, as opposed to magnifying their field of view directly. So that's an example of a visual search task, but of course, visual search is definitely not the only difficulty that low vision people have encountered in their daily life. So during my research, I've always been looking for the different challenges that low vision people have in their daily life. So for example, before we actually buy stuff in a grocery store, people need to get to the store first, which will involve a lot of mobility and navigation tasks. And stair navigation is one of the most dangerous mobility tasks that low vision people face. And the prior research has shown that low vision people have encountered a much higher injury rate of injuries and falls when walking on the stairs, as opposed to people who are sighted. And then what makes the stairs so difficult for people with low vision, and what technologies can be designed to facilitate this task for people with low vision? So to better understand the low vision people's experience in this task, still I started with an exploratory study observing 14 different low vision participants when they walk on different type of stairs, for example, indoor stairs, outdoor stairs, and also stairs made of different materials like wooden stairs and so on. And I find that surprisingly, the white cane that is widely used among people who are blind are not that often used by people who have low vision. So across my study, only 4 out of 14 low vision participants used a white cane. And instead, they used their, most of them, they actively used their functional vision when they walk on the stairs. And one of the most helpful information for them is contrast straps, which are these high contrast colors at the edge of the stairs. So a lot of participants try to look at these contrast straps to identify the existence and also the position of each step on the stairs. However, the problem is not all the stairs are accessible, and not all contrast straps are accessible. So many contrast straps, they actually don't have enough contrast, and also many stairs, they even don't have contrast straps at all, which made the stair navigation very difficult for people with low vision. So based on that, how can we design technologies for people with low vision? So considering that the contrast straps are the most helpful information, is all the information that low vision people are looking for when they walk on stairs, then what if we can design some mobile and personalized version of contrast straps, so that we can make the originally inaccessible stairs more accessible? So inspired by that idea, I designed Stairlight, which is a system based on projector technology. And here, the reason I choose projector-based AR device as opposed to AR glasses is because the current AR glasses, they always have very limited field of view, which is very difficult for people to use when they are conducting navigation tasks, because in the navigation task, people rely on their lower peripheral vision a lot, but it is actually not covered by most AR glasses, actually not covered by any AR glasses. So that's the reason why I designed Stairlight based on a projector-based system. So if the user hold this projector-based device, just like holding a flashlight, and then the system has a depth camera to automatically recognize the stair edges for the low vision user. And then the system can project back different visual highlights to increase the stair visibility. But the problem is, what visual highlights we should generate here? Should we simply just replicate these yellow contrast straps and generate the very similar yellow highlights on each of the stairs? Does each stair mean the same to a low vision user? So to answer that question, in my exploratory study, I also asked my low vision participants, how do they perceive each stair and how do they perceive different contrast straps? And based on their answers, I actually find that not all the stairs are the same. So, and among all the steps, only the first and the last stairs are the most important for people with low vision to locate. So after they can identify the first step, based on their muscle memory, they can probably just walk through the whole stairs until they encounter the end of the stair. And also, not all contrast strips are helpful for people with low vision. And many of them mentioned that if they see the same contrast strips on each of the stairs, it actually messed up with their depth perception and distracted them a lot. So most of them only want contrast strips on the top and the bottom of the stairs. So based on the user's experiences, I started to design the visual highlights for Stairlight. So while the design space is quite large, but my design usually relies on the user's needs and experiences that I distilled from my exploratory study. And specifically for this study, I have two findings. First, two design rules. So first, I need to emphasize the first and the last stairs. And also, we should probably minimize the distraction on the middle stairs. So based on these rules, I first use a different thickness of the highlights to distinguish the first and last stairs from the rest of the stairs. So you can see on the left of the image is a thick yellow highlights on the first step. And in contrast, for the middle stairs, I use the relatively thin stairs. So the thick highlights can better emphasize the first step and also the last step. And also, to enable a low vision person to notice the existence and also the exact position of the first step, I also designed different animations for the first stairs, so it can better attract the low vision person's attention. And this slide shows two examples. One is a flash, and the other is a movement animation. And also, I want to minimize the distraction on the middle stairs. So to do that, I provided different color alternatives for the highlights for the middle stairs, including a dull yellow color and also a blue color. And of course, the user can choose not to have any highlights on the middle stairs if they prefer to. So based on the design of these visual highlights, the user can select and also combine the different visual highlights when they walk on the stairs when using Stairlight. So this is a video showing how the user use Stairlight. So if they point the system to the stairs, the system can recognize the stairs. It's just like the interaction of the flashlight. And the system can recognize the most close 3 to 4 steps and project different visual highlights to the stairs and leading the user to the front. So this is a demonstration of how the system works. So still, the first question we want to answer is, how does the design work? Whether the visual highlights are effective enough for people with low vision. But the problem is, if we think about how we typically evaluate a system, we usually think about the accuracy or speed to measure the system performance. But the stair navigation task is a little different because it's a very dangerous task, and we probably don't care about whether the user can really run on the stairs, right? And the most important thing is we want to guarantee the user's safety. And then safety is actually a very tricky factor to measure because it's probably impossible. Like we measure how many times a low vision person will fall off the stairs when they are using our system, right? So it's very impossible. Then how should we do that? So to reasonably measure people's safety, as a first step, I instead measure the user's psychological security. So this is actually a term from psychology, which means how a person measure her environment to perceive her environment to be safe and out of threat. But of course, this psychological security is not the same with safety, right? Because if we think about the actual system, the system can have recognition errors if the user is using our system and they trust the system a lot and think they are safe. But if the system recognizes the information wrong and recognize the surrounding information and run and project the visual highlights at the wrong position, and it actually put the user at a more dangerous position. Then how can we address this problem? So to make the psychological security more close to the people's actual safety, I designed an evaluation study that to generate a relatively more ideal situation to make the people's psychological security closer to their actual safety. So how I designed the study is I put stationary projectors, two sets of stationary projectors on the top and the bottom of the stairs. And I use a method called Wizard of Oz, which is a very typical method in HCI. So a researcher acts as a computer, and by observing the participant behavior, the researcher can adjust the system manually based on the user's position on the stairs in our case. And I also ask the participant to hold a smartphone in their hands to simulate the experience of having a handheld device in their hand. So that's what you actually see in the demo video, is the user is actually holding this smartphone while walking on the stairs. So based on this setup, I recruited 12 low vision participants and asked them to navigate on the stairs in 2 conditions, including using stair light, and also as a baseline, I asked them to use their typical walking method. For example, if they want to use their white cane or if they want to hold on to the railings. So after the study, I asked the participants to give 7-point Likert skill scores to evaluate their psychological security. And this bar chart actually shows the participants' mean scores for the 2 conditions. The blue represents their typical walking method, and the yellow represents when they use stair light. And the result actually showed that stair light can significantly improve the participant's psychological security, and all participants felt much more confident when they're walking on the stairs with our system. So that's the evaluation of the design. And after that, of course, we'll need to implement the system. So this is still works in progress. So I combine a Kinect V2 with the projector, and I also attach an MU to track the user's hand motion so that no matter how the user's hand move during their walking process, we can still correct the projected result based on the user's behavior. And I also worked with the industrial designer to build this case via 3D printing and also laser cutting so that the user can hold all of these devices at the same time. So based on this hardware setup, I first calibrate the Kinect projector, the Kinect with the projector using Microsoft Room Alive SDK. And also based on that, based on the depth map from Kinect, I can recognize the use edge detection and also line and stair pattern recognition to recognize the position of the different stair edges, and then project back the results to the stairs. And we also combine the hand rotation information from the MU to correct the projection results. So this image actually shows the result of how we project the visual highlights to the real stairs. So based on this system, this system actually achieves a frame rate of 20 frames per second, which is pretty good if you think about if we render all the information on digital display. But the problem is now we are projecting the virtual information to the real environment. And also this environment itself is very challenging because the surface level changes happen very frequently. So when a person walk with this actual system, they still can feel a little bit lag from the system because of the recognition time. So as a next step to address this problem, I want to add a position tracking component into the system to compensate for the recognition delay. So how I want to do this is, first, I want to consider adding an indoor localization component to track the user's position. And another option is I'm thinking about using the state-of-the-art motion capturing system, for example, perceptual neuron. This is a full body tracking system that can, hopefully it can help me extract the user's absolute position on the stairs so that we can better refine the projection result for the system. So these are the two examples of my research on how I design augmented reality systems to enhance low vision people's visual ability in different daily tasks. So AR is a very powerful technology, and I believe that there are actually a lot of things we can do in terms of accessibility by using AR to enhance people's ability. So besides my current research on enhancing people's ability in very fundamental and individual level of tasks, for example, navigation, reading, visual search, these tasks, I think there are also a lot of things we can do. For example, I'm very interested in a more complex task that involve multiple users. For example, a social interaction, a work collaboration tasks. And I think it's very interesting to think about what's the role that AR will play, because that will also involve a lot the perceptions of the bystanders and also potential privacy and social acceptance problems. And also, besides people with low vision, whether we can extend my AR systems to different user groups, for example, people with different perceptual disabilities, for example, people with autism, people with learning disabilities. So this image is one of my projects that we try to use Magic Leap to recognize the facial expression of a person to help children with autism to better recognize other people's facial expression. So you can see we generate different virtual emojis to take the place of the other people's original head position, so that the kids with autism can better perceive this emoji to understand other people's facial expression. So, well, AR is a very powerful technology, but at the same time, this technology itself can also bring a lot of accessibility issues. And obviously, this technology currently is very vision dominant, which is very difficult for people with vision impairments to use, including both people who are blind and people with low vision. So besides designing systems to enhance people's visual ability, I'm also very interested in how we can shape this technology to make it more accessible and usable for people with diverse abilities. So, for example, some of my research also look into how we can design assistive technologies to enhance the accessibility of virtual reality technology. So one example is I designed a haptic controller. I call it cane controller because it simulates the real world cane interaction by generating different force and audio feedback in a virtual space to enable blind people to navigate a virtual reality environment. And also another one is focused on people with low vision. It's called Seeing VR, where I designed 14 different low vision tools to enable low vision people to better perceive different VR scenes. So, well, there have been these different work I've done to enhance the accessibility of virtual reality, but I do believe there are a lot of work to do for augmented reality, because AR is not only about the virtual space, it's actually a combination between the virtual space and the physical space. So how can we, what information from the virtual and physical space we should accessibly convey to people with disabilities, and how can we convey the relationship between these two worlds? And also, besides the technology, besides making the technology itself accessible, how can we also maintain the immersive experience that AR and VR are supposed to provide for people? So I think these are all very important and interesting questions that I want to look into in the future. So by saying that, because this is a very large field, of course, I won't be able to work on this research by myself. So I'm actually looking for PhD students who are interested in this direction to join me. So I'm not very sure about the distribution of the audience, but if you're interested in accessibility or AR, VR research, and if you want to consider a PhD position, please feel free to contact me. Yeah, so today I talk about two of my research projects, QC and Starlight, which are all AR systems about how we can provide direct visual augmentations to help people with low vision to perceive and understand the surrounding environment. So in general, I myself, I do believe in the future of augmented and virtual reality. And I believe that maybe in the next 20 years, everyone will wear smart glasses and the environment will be embedded with projectors so that all the physical surfaces will be interactive. And to achieve that goal in the future, I think it is very important for us to think about how to best leverage and also shape this technology to make it better serve and empower people with diverse abilities. Yeah, so that's all my talk. So now I'm open to answer questions.
Thank you so much, Yuhong. That was awesome. So, hey everyone, we'll now open up the floor for questions. Those of you on the YouTube stream, several of you, please type your questions into the chat on YouTube, and Stacy will ask them here in the room. Just to kick off here, for those in the room, does anyone have a question for Yuhong? Great presentation, thank you. I'll start with one just to kick it off. Yuhong, I was curious for you mentioned, at the start, there's lots of different types of low vision users or people. There's, all these different types of diagnoses and ways that the field of vision can be affected. Starting with QC, and you were showing the black and gray flashing solution. Were there any differences between preferences for people with certain categories of low vision for one solution or the other? Was that part of the research?
Yeah, it is actually. So let me get back to my slides with all the Q examples. So that's actually one of the research goal as well, besides we want to validate the effectiveness of the Qs. So this is a very good question actually, because it's tricky because, even though low vision people there are many different low vision condition categories, but actually a low vision person, they usually have very mixed visual condition. They can have both very blurry vision and also lose part of their field of view. So at the beginning, we actually didn't expect we can find any specific patterns. So that's not the major goal, but from the study, we do find people have some preference patterns. For example, the guideline and spotlight. So I didn't go to details of the different design, but here, if you look at the guideline, so it's very simple, it's very subtle. We just connected the center of the target to the center of the user's field of view. And also the spotlight is we make the background all grayscale, but only keep the original color of the target. So these two are mostly preferred by people with relatively good vision, not really a specific visual condition, but relatively people who have a better field of view and better visual acuity, because these designs are subtle, so it won't distract them a lot, but still they are able to notice these visual cues to find the target. But as opposed to these relatively subtle design, if you look at this sun rays, the third one in the first row, so there are 8 lines extending from the border of the target to the border of the user's full field of view. So this one actually are, and also the flash one. So these two are relatively like dramatic cues, but they are very effective to people with ultra low vision, which means they usually have a very low visual acuity. And for the sun rays, it's actually used a lot by people who have field of view loss. So not necessarily a peripheral vision loss. A lot of people, they have blind spots inside of their vision, but it's really hard for us to know which part of the peripheral vision they can, which part of their field of view they actually have and not have. That's why with all these 8 lines, as long as the user can locate 2 of them, they can follow the lines to the target. So these two are actually very effective for people with severe low vision. But unfortunately, movement, none of my participants selected it because it's just too much, too overwhelming for it, especially this location actually, this movement, this rotation actually disabled them from seeing the details of the product. So even though they know where it is, but they still want to, verify this is the exact target that they are looking for. So this one is not a very successful design, but of course it doesn't mean that movement in general is not a good cue, because it's actually people's peripheral vision are very sensitive to different types of movement, but probably rotation is not the best way to convey it. Yeah.
Oh, thank you so much. That was great, and I'm glad you went into the detail of these. It's really interesting. Do we have any questions in the room? And you can type them into the chat too. Yeah.
Oh, Thomas, I've got a question here. It's David. Can you hear us?
Go ahead.
All right. When you looked at the stair light, you can hear us clear? Excellent.
Yeah.
When you looked at the stair light, talked about safety. How did you discount people perhaps haven't had sufficient trainings of a long cane?
I'm not sure I hear the question clearly. Are you asking when I'm evaluating the stair light, how do I do I deal with how to train the participants when using the system?
No, it's more a case of have they actually used a long cane properly?
Oh, whether they can
Not
use
sure
a
my question
wide
is
cam
coming through clearly. Yeah, when I work in the area of vision impairment, and one of the issues with stairs, we look at, does the person actually use them to identify the stairs? You mentioned very small cohort who actually did. Is that correct?
Yeah.
So in terms of their safety, how did you discount if these guys haven't the cane properly or haven't had the sufficient training stairs?
Oh, so you're saying how can I decide whether the participants get a appropriate training of the wide cane, whether that's a reason why they didn't use the wide cane. So we didn't verify that, unfortunately, but so during our study, the first thing they come to our lab to conduct the study is we ask them what tools they use. And so four of them decided to use the wide cane in our study. but a lot of them actually have the white cane, and they have. We did ask them like whether they know how to use the white cane, and most of them, it actually depends, because a lot of low vision people, it's not only about whether they have a proper training of the white cane, is also about whether they want to use the white cane. I'm not saying that white cane is not an effective tool for people with low vision, and the fact is they probably are very effective. But the truth is, a lot of them even though they know they can use the white cane, but they don't want to, because a lot of them, they actually, first of all, they have jobs, and they don't want to expose their disability related to low vision. And also, if a lot of people mention that if they're working with the white cane, they can also be targets of the some potential crime. A lot of these, so many of them, because they still have a functional vision, so they see them themselves of a person that being able to use their vision, and they also don't want to use the white cane because of their own preferences. There are a lot of like personal emotions and social acceptance there. So that's why the reason that we design Stairlight is not really designed to replace the white cane. That's why in our study, we also allow people to use the white cane together, maybe with the Stairlight if they want to. So the major goal of this project is more about can we provide another alternative if people not want to use the white cane in their daily life.
Thank you. While we're waiting, I had another question related to the stair model. Was you showed the colors of the dull yellow and blue as different colors to use, for identifying the stairs. Same question related to your previous project, but was there preferences based off of, low vision diagnosis for certain colors or?
Yeah, that's a really good question. So very different from QC, where we find that people actually have very different preferences. For Stairlight, actually people have a much more consistent preference patterns across most of the participants, is the combination of using a bright yellow thick highlight on the first and last stairs, and use yellow thick thin highlights on the middle of the stairs. Is this very basic combination here. So this is what the most user would prefer. So even though there are some users, they do use a blue color, but blue and dull yellow, they are challenging colors for some of the low vision participants. That's why they want, they still prefer this relatively bright yellow color on the stairs. And also one interesting thing is, even though from the exploratory study, many people mentioned they don't want highlights on the middle stairs, but when we have people to decide what they actually want use in the system, they actually, I think 13 of them, they decide to use highlights on the middle stairs, because if you look at the demo, you can see, because if they see this dynamic process of the highlights appearing on the stairs, people actually feel very safe about seeing these feedback all the time. So if they don't see them, they feel very insecure.
Mm-hmm. Thank you. Any other questions in the audience?
Yes, please.
Yes.
A very great presentation. Thank you very much. I wish I were a student so I could join you. The example of the cane that you mentioned was kind of fascinating to me. Is that something that you've built out, and what kind of mechanism, if so, would you use to execute that kind of VR cane?
Oh, you mean the controller at the end? So that is actually a brake mechanism that people wear right in front of their body. So this one. So if you look at the image, so right in front of the user is a brake mechanism, and there is a slider extended to the front, and then there is this and we attach.
Yuhong, I think the slide isn't showing for the one that you're talking about. So just can you check? It's not showing on my screen.
Oh, that's weird.
Maybe it just stopped.
Should
updating. Okay, sorry. I think it's okay just to talk it through. I just wanted to make sure though, like if there was a way to fix it easily. It's still showing the stairs for me. Might be. Yeah,
that's weird because I did adjust it, but so it's basically a controller that people can wear right in front of them. So it's a brake mechanism. So it's and there we put a slider extended, a 3D printed slider extended from this brake mechanism, and this slider connects to half of a real webcam. So if the user sweep this controller by holding this half webcam, and then if the virtual objects in the virtual environment was hit by the virtual cam represented by the actual controller, and then this brake mechanism will shut on so that the user will feel this force feedback, because this brake mechanism will stop them sweeping. So, and then they will get this force feedback just like they hit a real object. And also at the same time, we generate a spatial audio to simulate the different sound when the cane hits on different materials. And we also attach a vibrator, a voice coil to our controller so that it can generate different vibration patterns to simulate when the virtual cane sweeps on different virtual materials like grass, carpet, concrete, and so on.
Very cool. Thank you.
I'm going to ask one more question since I don't hear another one, but I was curious about the speech recognition. You know, adding speech recognition to VR solutions is, since it's not really built in to most of the platforms, or some of the platforms it is, some isn't. I was just curious what was your process to get like speech recognition for QC, or just when you want to use speech recognition, do you have a preferred technology for that?
Yeah, so honestly, I didn't implement a QC on like using, for example, Unity, using like typical VR or AR engine. So what I use, I just build this based on basic programming technology, because it's more of a custom device, right? I attach a webcam with Oculus Rift, so I just see Oculus as an external display. So I just render all of these information on my computer based on, I think based on Python, because we also use a lot of deep learning model. So Python would be the easiest programming language to do that. And we also use the Google voice recognition engine to do for this speech component, but it's not really embedded into Unity, if that's what you're curious about. But in this prototype, we just use like basic programming language and generate image on the computer display and add it to the Oculus display, using it as an external display.
Yeah, thank you. That makes sense. Yeah, thank you. We have time for a couple more questions, and if we don't have questions, we'll move to our social component. Does anyone else have any questions in the room? All right, well, I want to say thank you so much to Yuhong Zhao for the presentation today. It's tons of amazing research, and really look forward to the continued work you do at University of Wisconsin. If anyone in here is looking for PhD students, yeah, I can definitely tell there's going to be lots of exciting research continuing from you and your students. So thank you so much for the
Thank you.
presentation today. I want to close with, I'm Thomas Logan from Equal Entry, the organizer of this event. We want to say thank you very much to Jolie McPhee from the Internet Society of New York for streaming us to YouTube and helping us maintain an accurate record of all the presentations we have here. We want to say thank you to Stanley Sakai, the captioner for our event tonight. And we want to thank all of you for coming and participating. We will be having our next event in November. We don't have it posted on the Meetup site yet, but it will be related to haptics and touch being used for accessibility use cases in virtual reality. So stay tuned for that one. And for now, we'll end the stream and end the captioning, but you can